Imagine you're aboard a spaceship that can continually accelerate. Starting from Earth and reaching or exceeding the speed of light, would time come to a complete stop? What would you see and feel? Would you gain immortality, or would your consciousness disappear entirely? This isn't a science fiction scenario, but rather a fundamental cosmic law formulated by Einstein in the form of the Lorentz transformation. Let's take a look at some visual comparisons. At 10% of the speed of light, you experience 1 year, while Earth experiences a year and about 1.8 days. At 50% of the speed of light, your 1 year equals a year and 47 days on Earth. At 90% of the speed of light, your 1 year equals 2.2 years on Earth. At 99.9% of the speed of light, time dilation becomes 22 times. Your 1 year equals 22 years on Earth. As you approach the speed of light, the time differences become more extreme. So, the question is, what happens when you reach the speed of light? Does time come to a halt? Let's start with a question. Do you think time is fair? Does one day always have 24 hours, and 1 hour always have 60 minutes, regardless of who you are? Before Einstein, most people thought so. Newtonian physics was based on this assumption. Time was like a cosmic clock, the same for everyone. But in 1905, at the age of 26, Einstein said, "No, that's not correct. Time is not absolute. Instead, it is personalized. The faster you move, the slower your time passes." This is not metaphysics. It is backed by experiments that defy common sense. For example, if you throw a ball on a high-speed train, the ball's velocity is the sum of the train's speed and your throwing speed. This is classical physics as we know it. But light doesn't behave this way. Whether you are running towards the light source or away from it, the speed of light remains constant at 300,000 kilometers per second, as if light has a speed compulsion, always staying the same. In 1887, two scientists conducted the famous Michelson-Morley experiment, attempting to measure whether the speed of light would vary as Earth orbited the Sun. After hundreds of measurements, the result was a zero result. This stunned the scientific community. Finally, Einstein explained, "Don't worry about the speed of light. Instead, rethink our understanding of space and time. If the speed of light must remain constant, then space-time itself must be flexible." This is where time dilation comes from. The time for a moving object slows down. In fact, we encounter this principle every day, like in our GPS systems. Satellites orbit the Earth at about 14,000 kilometers per hour. Due to time dilation, clocks on satellites run 7 microseconds slower per day than those on Earth. While this may seem small, if not calibrated, the GPS would be off by 11 kilometers every day. You might end up driving into a river. Now, let's answer the original question. If you truly reached the speed of light, time would stop completely. But what would it feel like? The serious answer: objects with mass, like you, me, or a spaceship, can never reach the speed of light. Why? There's a deadlock in Einstein's formula. The closer an object gets to the speed of light, the greater its relativistic mass becomes. As it approaches the speed of light, the mass becomes infinitely large. To accelerate an infinitely massive object, you would need infinite energy, which is simply impossible in our universe. For example, if you try to accelerate a bottle of ordinary water to the speed of light, the energy required would be equivalent to the total energy output of all man-made satellites for 1,000 years. Far more than a human-made spaceship could ever produce. The most powerful particle accelerators today, like the LHC at CERN, can only accelerate protons to 99.99999% of the speed of light. And even that last 0.0000001% would require 10 times more energy and still be unattainable. This is the law of the universe, an impenetrable wall. There's another straightforward piece of evidence. Muons, subatomic particles with a half-life of only 2.2 microseconds. Even if they're traveling close to the speed of light, they shouldn't reach the Earth, according to their lifespan. However, we catch plenty of them on Earth. Why? It's because of time dilation. From our perspective, the muons' time slows down, so they live longer and can reach the surface. But what about light itself? Photons, which move at the speed of light, experience no time. For them, the journey from the Sun to the Earth, which takes us about 8 minutes, happens in an instant. Even light that has traveled for 13.8 billion years since the Big Bang experiences no passage of time. The journey happens instantaneously. Now, let's revisit the original question. What would happen if you were aboard a spaceship moving at close to the speed of light? Let's assume there's no energy limit and take you through 6 stages of an extreme journey. Stage 1. 10% of the speed of light. Stars in front of you shift slightly to blue, and stars behind you shift red. This is the Doppler effect. Light waves compress or elongate. Your watch ticks normally, but when you try to communicate with Earth, their responses become slower. This isn't a communication problem. Earth's time is literally running faster. Stage 2. 50% of the speed of light. The stars ahead of you compress into a light tunnel. All light beams converge in the direction of travel, which is called light aberration. The space behind you gradually turns dark as the light shifts beyond the visible spectrum. At this stage, 10 minutes for you equals 11 minutes and 8 seconds on Earth. Stage 3. 90% of the speed of light. The light tunnel becomes blindingly bright, and even cosmic microwave background radiation, the afterglow of the Big Bang, gets compressed into visible light. You're essentially looking back in time. Time dilation is significant. For every day you experience, 2.2 days pass on Earth. If you return after a year, your friends will be 2.2 years older. Stage 4. 99.9% of the speed of light. The greatest danger is no longer time, but interstellar dust. What were once harmless hydrogen atoms now become dense bullets that could puncture your ship, requiring heavy shielding. Time dilation has increased. For every year you experience, 22 years pass on Earth. After 10 years, Earth will have aged 220 years. A 10-year nap could leave the world dramatically changed. Stage 5. Nearing the speed of light, your watch appears frozen, but you feel no different. Your heart rate and thoughts are slowed in sync with time. If you spent 26,000 years flying across the Milky Way, you'd only age 52 years. But when you return to Earth, 26,000 years would have passed. Humanity might have already entered an interstellar civilization, changing multiple times over. Stage 6. At the speed of light. At this point, your mass becomes infinite, and time completely stops. You no longer feel anything or even have any sense of consciousness. You transform into pure energy, like a photon. Many people mistakenly think that traveling faster than light would allow you to travel backward in time. But in Einstein's framework, faster than light travel would cause causal relationships to break down, seeing the effect before the cause. The universe doesn't allow this. Scientists have been searching for faster than light particles for decades, but none have been found. All experiments indicate that light speed is the ultimate limit for information transfer and causal relationships. So, is near-light speed travel possible in the future? The most promising method today is solar sails, large sails propelled by powerful lasers. These sails could theoretically reach 20% of the speed of light. It would take about 20 years to reach Proxima Centauri, the closest star to our solar system. However, this would cause the astronauts to age around 19 years, with time dilation slowing them by about 1%. This project would require laser power equivalent to the entire global energy output, meaning it will likely take at least 50 years or more before such missions become feasible. Finally, I'd like to ask, if you had the chance to travel at near light speeds, who would you want to take with you? Which planet would you most like to visit? Feel free to share your answer.